This is Thursday the 1st of April, April Fool's Day. It's also the last day of the semester at King's, and this is the last video lecture for the module Discrete Mathematics. I'm going to cover the short section 11.3 in the lecture notes. I shan't be saying anything about the exams this week, I'll be putting material on Keats after Easter, so please don't ask me about the exam until I've put material and you've had a chance to look at it. There'll be things to help you prepare for the exam material, and there'll also be a live session in the week beginning the 26th of April, but you'll have ample opportunity to study questions before then. So we've been talking this week about the RSA algorithm, and that's based very much on the notion of prime numbers. The public key involves the product of two prime numbers, P and Q, and these are getting larger and larger. Currently at least 2,000 bits is needed to define these prime numbers, and it becomes very difficult actually at that level to test whether a given number is prime. So one tends to rely on a sort of probabilistic assessment of whether the number is prime without knowing for certain whether it's prime. It's a bit like detecting maybe fine art nowadays. You can't be absolutely certain that a painting is by so-and-so painter. Anyway, so this section is really devoted to the idea of trying to work out, at least with high probability, whether a given number is prime. We'll be dealing obviously with smaller numbers, but the material is quite interesting. Again, you're likely to find this easier if you've done Introduction to Number Theory, but I hope everyone can manage with this section. So I want to start with a small result, a lemma, which really should have been done in the first week of the course, actually. If I were redesigning the course, I put it there. It's just this simple fact that if you consider numbers of the form a power of 2 plus 1, they can only be prime if the exponent k is itself a power of 2. Now, we talked a lot in the first week about powers of 2 when we were talking about decimal expansions. But this is an interesting result. So if you take any power of 2 plus 1, of course you need the plus 1 to make it an odd number, otherwise there's no hope it will be prime. On the whole, it won't be prime unless k is a power of 2. And it's quite easy to prove that result. Here's a proof. It's partly by example, but you can easily write out a formal proof if you understand this example. So to say that k is a power of 2, it's the same thing as saying that k has no odd, the integer k has no odd factors. So suppose k does have an odd factor. Suppose k is equal to I times j, in which the integer j is odd. And I'm going to set, for shorthand, I'm going to let x denote 2 to the power I. So j is odd. The complementary factor I, 2 to the power I, we call that x as an abbreviation. Then I claim that x plus 1 is actually a factor of 2 to the k. X plus 1 is a factor of 2 to the k plus 1. Why is that? Well, it really follows actually from the remainder theorem. Let me illustrate it with the case in which k is 20. So 20 has an odd factor, it's not a power of 2, it has an odd factor, 5. So let's take j to be 5. That means x is 2 to the power 4, which is 16. But you see, 2 to the k plus 1, 2 to the 20 plus 1, that's the same thing as x to the 5 plus 1. And we know that when you have an odd power of x plus 1, that will always have x plus 1 as a factor. That follows from the remainder theorem. So that's where the oddness comes in. So x to the 5 plus 1 has x plus 1 as a factor. I don't really know what the rest is, but of course if you want to know, it's just the alternating sum of these remaining powers. x plus 1 is a factor, but that proves my claim, because x plus 1 is actually, in this case, 17, 16 plus 1. So 17 is a factor of 2 to the 20 plus 1. So, I mean, that proof will work in general whenever k has an odd factor. So that's an interesting result. And this, of course, relates to the end of the last lecture. The reason I've started with this, I should have said, is because I finished the end of the last lecture talking about the fourth Fermat number. So let me give you this definition then. The nth Fermat number is 2 to the power 2 to the n plus 1. So we know that k has to be a power of 2 if there's any hope of getting a prime number. So we're interested in prime numbers, so we might want to ask, suppose we take 2 to the power 2 to the n plus 1. Maybe that's always a prime number. That's what Fermat thought, actually, but it's not. The first few numbers, starting with n is equal to 0, are 3, 5, 17, 257, and then the number we discussed at the end of the last lecture that's often used as an exponent for RSA is 65537. So I explained in the public key business that that's often encoded using base 4 as part of a public key by the characters AQ, AB, which just stands for 2 to the power 16 plus 1, and B giving 1 at the end. Now it turns out that the next number in the sequence, so this I called this F4 actually. I shouldn't have used F4 because that sounds like Fibonacci number, really, so I won't use that notation anymore. But the fifth Fermat number is this number here, and it turns out that's not prime. It's divisible by 641. And in fact, then following that, all the known, I think up to about the 11th Fermat number or something, they're all known to be, no other Fermat numbers are known to be prime. So they get very big very rapidly, and the next few are all known to be composite numbers, not primes. So it's not known whether any other Fermat number is prime. Maybe it's not, maybe the fourth one is the last one, we don't know. But I hope this little problem explains why we're interested in trying to assess whether or not a number is prime, because as soon as the number gets very big, it's very difficult to factorise it. That's the whole point of the RSA security. That's why RSA works, because it's very hard to factorise prime numbers, large prime numbers. So with this problem in mind, of course, the real use will be for trying to find prime numbers to use for RSA. But in a sense, this is also an interesting problem, the problem of Fermat numbers. So I want to remind you the starting point for today's lecture mathematically is Fermat's little theorem. So you must remember what we're going to do today just really generalizes the result of Fermat's little theorem. So Fermat's little theorem tells us, remember, that if we have a prime number and we take an integer a between p, I've called it p, and this is what follows. So if p is a prime number and we take an integer a strictly between 0 and p, then we know that a to the power p minus 1 is equal to 1 mod p. That's Fermat's little theorem. It follows easily from group theory because all the non-zero congruence classes form a group under multiplication. So if you raise the p minus 1 of them, because we run the non-zero ones, we run from 1 to p minus 1. So when you take any element of a group to the power, the size of the group, you get the identity. That's why Fermat's little theorem holds. Now, we also saw, if you remember, one or two of you asked me about this to explain the table. At the end of the third video, I think, or the third section anyway, in week 1, I had some slides in which I finished with a table of looking at powers 2 to the 2 to the n minus 1, where n ran from actually, I think, 1 to 600. And we found two numbers, namely 341 and 561, for which it was true that Fermat's little theorem holds, even though these numbers are not prime numbers. These are both composite numbers. Obviously, the first one's divisible by, well, they're both divisible by 11, as you can see. Nonetheless, it's true that for when a is 2, we were just doing the case of what's called base 2, 2 to the n minus 1 was equal to 1 mod n. So here there's a confusion I see between n and p, but I hope it's clear. If you like, for general n, well, I mean, what I've written is true, but if for general n, we'd have to, if n is not prime, I use the symbol n rather than p. So what I'm saying is that for these numbers, a to the n minus 1 is equivalent to 1, or equal to 1, I can say, mod n, even though these numbers, these two numbers, are not prime. And in fact, there's a third number. We only went up to 600, but if you go up to 1,000, you'll find there's just one more number for which a to the n minus 1 is equivalent to 1 mod n. So what you see from this is that actually Fermat's little theorem is incredibly good at detecting prime numbers. We know that if a number is prime, then a to the n minus 1 has to be 1 mod n. But if that condition holds, it's pretty certain that the number, even if we take a to be 2, it's pretty certain that the number is prime. Pretty certain in the sense that we only miss out on 3 cases, even if we go up to 1,000. Okay, so that's the background. That's Fermat's little theorem. Now I want to generalize this with a result which is called Miller's test. It was later generalized to make it probabilistic, sometimes called the Miller-Rabin test, but I just want to talk about the simpler version, which was really discovered by Gary Miller in the 1970s, which is the same decade in which RSA was conceived. Not to be confused with something called the Miller test, which is to do with someone called Marvin Miller, who published pornography in California. That's a completely different thing you can look up about online. This is Gary Miller's test. So, first of all, before I tell you what the test is, let me remind you of another lemma. And this says the following: if p is a prime number, and we want to extract a square root of 1, so x squared is 1 mod p, then we know with certainty that x has to be either plus 1 or minus 1 mod p. Don't forget that when we're working mod p, minus 1 is the same thing, mod p, as p minus 1. So when I say minus 1, if you prefer to use a positive number, you have to use p minus 1. And the proof of this is almost immediate. I've given it before, I think, in the first week. If to say that x squared is 1 mod p means that p divides x squared minus 1. So you can factorize x squared minus 1 into x minus 1 times x plus 1, and therefore p divides x minus 1 or p divides x plus 1. That's the property of a prime number. You can't, prime number, it divides a product of two numbers. So as I say, remember, I'm using the fact that this is x minus 1 times x plus 1. And if a prime divides the product of two numbers, it has to divide one of those two numbers. It can't be split up between the two factors. So one of these things holds, and that's the same thing as saying p is equivalent to plus 1 in the first case or minus 1 in the second case. So this is a key lemma. So it will allow us to understand whether or not we're dealing with a prime number. So Now let's look at these three numbers, these three exceptions that sort of passed, these numbers in a sense passed Fermat's test, one could say, because Fermat's little theorem told us that these numbers behave as if they're prime. So let me just remind you again what, as I confused you probably with N and P, let me remind you what Fermat's little theorem says about these numbers. The first one, for example, it says that I could take any number, we were doing base 2. So Fermat's little theorem to base 2 tells us that 2 to the n minus 1, that's 340, is as if it were prime, as if 341 were prime, is equivalent to 1 mod 341. That's what Fermat's little theorem tells us. And so as far as base 2, we say base 2, nothing to do really with sort of binary. We're working here to base 2 as our integer a. We can say that 341 behaves, as far as Fermat is concerned, Fermat's little theorem is concerned, it behaves as if it's a prime number. Similarly, 561 and 645. However, let's try and sort of take more square roots, essentially. So let's consider 340, which is the exponent here. You see, 2 to the power 340, that's the square of something. I could take 2 to the 170 and square that. Because 340 is an even number, when I square this, I get 2 to the 340, which we know is 1. So we're in exactly the situation now of the lemma. We're asking, we can think of this as being x. X squared is now equal to 1 mod 341. So is x plus 1 or minus 1? That's the question. Since 341 is not a prime number, we can't be certain. Okay, well, it turns out that it is equal to 1. Turns out this is equal to 1. So that doesn't really tell us anything new. But we can keep going. We can now say, I can keep going. I can say, given that this is equal to 1, let's now take a square root of 2 to the 170. Half of 170 is 85. So I can replace this with 85. And I can ask, what about if now x is 2 to the 85? Is x plus 1 or minus 1? And the answer is no, because 2 to the 85 is actually 32 mod 341, which is neither 1 nor minus 1. Minus 1 would be 340. So in this case, it shows you that 341 can't be a prime number because it fails this lemma. And that's what Gary Miller's test is all about. We would say that this number 341 fails Miller's test because Miller's test involves taking successive square roots as far as you can, as long as you can keep dividing the exponent by 2. Sometimes you can't divide it at all because you'll always be able to divide it by 1 power of 2 because the n minus 1 is always an even number. But maybe you can't go further than that. Okay, so let me just quickly look at the other two numbers, the other two exceptions. Now it turns out that in the case of 561, we could divide this by lots of powers of 2 and we could keep going. There'd be lots of things to check because half of 560 is 280, then we get 140, 70, and then it becomes odd. So we could go all the way down to 35, and so there would be sort of 4 things to check. But it turns out that although when we half it again we get 1, when we half that, just as in the first case, we get something which is not plus or minus 1. So that also shows us that 561 is not a prime number. And it's even easier for 644 because when we half that, we get 322, and already it turns out that 2 to the power 322 is neither 1 nor minus 1 mod 645. So in other words, by using this lemma, we can see, without having to factorize these numbers. Now, of course, these numbers are very easily factorized, but the principle would work for much, much bigger numbers. We can apply this test much more easily than we could trying to factorize the numbers. So what we're saying, what I'm trying to tell you here, is that these exceptions, now we were just working to base 2 here. We could have chosen any other exponent up to n minus 1, or up to about half n. Here we're just using 2 because it's very easy to compute powers of 2. It's harder to compute powers of 3 by hand, 4 and 5 and so on, but even by hand one can compute quite high powers of 2. So the point is, I explained earlier that these are the only 3 exceptions really between 1 and 1,000 which pass Fermat's test that are not prime numbers. Fermat's little theorem sort of, the result holds even though these are not prime numbers. But all these 3 numbers, because of what I've said here, when you take successive square roots of the exponents, you don't always get plus or minus 1. So to that extent, we say that they fail Miller's test. The Miller's test is a matter of applying the lemma and checking as much as you can when you keep dividing the exponent by 2, which is equivalent to extracting square roots, that you always get plus or minus 1 mod n. So here is the get rid of the squiggles. Here is the definition of Miller's test. And it's probably hard to grasp this during the lecture, but I've written it down so that you can look more carefully afterwards. So, as I say, it's based upon Fermat's little theorem is a matter of we're fixing a base A. Okay, so it could be 2, or it could be anything up to n minus 1. We're fixing that base A, that integer A. Before I was just talking about 2, but this whole theory works for any such integer. We fix that integer. And we know that Fermat's little theorem is telling us something about a to the n minus 1. If n is prime, then a to the n minus 1 is 1 mod n. But for Miller's test, we take square roots of a to the n minus 1. So that's equivalent to actually seeing how many powers of 2 divide n minus 1. So in the last case of 644, we had 2 powers of 2 because 644 is divisible by, what can we go? We can divide it by 4, okay. But we only had to divide it by 2 to get a contradiction. Anyway, we divide n minus 1 by as many powers of 2 as we can, and we keep looking at what happens when we take these square roots. Do they equal plus or minus 1 mod n? So there are 2 things that could happen. If at some point we get a minus 1, then we can't really say anything for the square root of that, because we're not going to say anything about the square root of minus 1 mod n. So if we get a minus 1 at some point, and I'll give you a table in a moment to explain this, then we say that the integer n passes Miller's test. It looks as if it's a prime number. So if we get minus 1 anywhere on the way, or the other scenario is that we go all the way down to the lowest, we keep taking square roots and we still have 1 at the end of the day. So we have 1 or minus 1. If we take a to the power m, which is the smallest square root we can find, so we keep dividing the exponent by 2 and eventually we get an odd number. So if a to the m is 1 mod n, then that's okay, because all the squares of that will also all be 1. Or if it's minus 1, it's okay. Or if it's minus 1 anywhere else, it's okay. In those circumstances, it's looking as if the integer n is prime. So we say that it passes Miller's test. And in fact, we also say that n is a strong pseudo-prime. So let me explain this. As I say, it's probably hard to grasp it in abstract. Let me explain it with reference to a table. So for this purpose, I'm going to go back, this final slide, I'm going to go back to the lecture notes and look at an example which is studied there. Although I think maybe I've explained this a bit more carefully on this slide. The example consists of the integer 217. This is obviously not a prime number because it's obviously divisible by 7. In fact, it's equal to 7 times 31. Now, supposing we want to find what is a square root of 1. Does this have, if we have x squared is equal to 1, x squared is equal to 1 mod 217, what is x? So x squared is equal to 1 mod 217, what is x? Well, 217 is not a prime number, so in these circumstances, there will be other solutions for x. And I'll tell you how to get the other. There's going to be a sort of couple of other solutions. And you can get them by using Euclid's extended algorithm. Namely, what you do is you take the two factors. I'm talking about two factors here, numbers that have just two prime factors, as in our essay. We apply Euclid's extended algorithm. Here you can sort of do it by inspection because 9 sevenths are 63, twice 31 is 62. So 9 sevenths minus twice times 31 is 1, which is the greatest common divisor, obviously, because these are prime numbers. Now you double that. So something we've never done before. If the greatest common divisor is 1, you can double the equation here and say that 2 is equal to this combination here of 7 and 31, and that allows you to write 2 as 126 minus 124, in which 7 divides the first number 126 and 31 divides the second number 124. And said another way, that means that 217, which is the product of those two primes, divides. You split the difference here and you take the difference of 125 as being the number halfway between one. That's why I doubled it, halfway between 126 and 124, and 125 there, it's hidden there. So what I'm telling you therefore is that 217 divides the product of 126 and 124 because of this observation here. Because 7 divides the first one, 7 divides the 126, and 31 divides 124. So therefore, 217 divides the product. But because 217 is not prime, this time we can split its factors between the two numbers we have here, 126 and 124. So in other words, we're saying that 217 divides 125 squared minus 1. Because this product here becomes 125 squared minus 1. And that means we found a different square root. By splitting the prime factors of n across these two factors, we found another square root. And the other square root is 125. So minus that must also be a square root. And in fact, minus that is a smaller number, mod 217, it's 92. So we've actually discovered that plus or minus 92, which is the same thing as minus or plus 125, is also a square root of 1, mod 217. Of course, 1 and minus 1 are still square roots, minus 1 being 216. So we've now got actually 4 square roots of 1 mod 217. So the answer to this question is given here. With including the minus, plus or minus 1. So I didn't really need to know that, but it's useful to know that when you have an integer that's product of two primes, you have these alternative square roots of plus or minus of 1, which you obtain by splitting the prime factors up. So let me now give you another example. This is the example really in the lecture notes of Miller's test in practice. So in this example, I'm no longer restricting to base 2. I've gone up to from 2 all the way up to integer 10. This is my base. This value across the top is called the base when you do these tests, either with Fermat's little theorem or Miller's test. The integer a you're taking is called the base. So what I'm doing here is I've fixed this integer n, which we happen to know is not prime, and I want to know whether Fermat or whether Miller detects the fact that it's not prime. Well, n was not one of our exceptions for Fermat's, for base 2, for Fermat's little theorem base 2. So we know that base 2 already we're not going to get a 1 here, because had I got a 1 here, it would have been one of our exceptions, but it wasn't. So we already know that we don't get a 1 here. And in fact, we don't get a 1 for even going up to 10. We only get a 1 to base 5 or base 6. So what that means is that as long as we choose a base that's not 5 or 6, at least up to 10, even Fermat's little theorem will tell us that this number is not prime. If we were in doubt, suppose we're sort of blind to be able to factorise it, the Fermat test, if you like, provided we have, what one says is that Fermat's test fails, this integer fails Fermat's test to base 2, 3, 4, 7, 8, 9, 10, but it passes it to base 5 and 6. Now the problem is that, can we do better than that with Miller's test? So to apply Miller's test, what do we have to do? I'll do it quickly again. We take n minus 1, which here is 216, and we take halving the exponent as far as we can. And here we can go quite a way again. We can halve it 3 times. So we can go to 108, 54, or 27. You keep halving it until you get an odd number. Then, of course, you can't halve it anymore, so you have to stop. So you keep halving the exponent. By the way, this table is the other way around. I might change it in the lecture notes. In the lecture notes, I started with the row at the bottom. But anyway, so I always look down really from the top. So if we let's look at base 5. So what happens with base 5 is that the number, as far as Fermat is concerned, this number 217 looks as if it's prime because it satisfies that 5 to the 216, this table is telling me that 5 to the power 216 is indeed congruent to 1 mod 217. So in that sense, it passes Fermat's test, even though it's not a prime number. But if we take a square root and ask 5 to the power 108, so suppose we look at 5 to the power 108, well, it turns out that's also 1. It could have been minus 1. It's actually 1. And so we keep going. Given it's 1, I don't want to take square roots of minus 1, but given it's 1, we can take a square root again and go to 5 to the power 54. And it turns out that that's also 1. Okay. So I can take a square root again. This is what I'm doing for Miller's test. I take a square root again. It's my last chance here. 5 to the power 27. And it turns out that's not equal to 1, and it's not equal to minus 1 either. It's equal to minus 92. It has to be, it has to be plus or minus 92. That was the calculation we already did, but it's not plus or minus 1. So therefore, this number can't be prime, because according to our lemma, if we take a square root of 1, we would have to get plus or minus 1. 5 to the 27 being a square root of 5 to the power 54. So it fails Miller's test. This number fails Miller's test, and it tells us that this number, being 217, fails Miller's test to base 5. Just using the exponent, just using the base number a is equal to 5, we've detected that 217 is not prime, using Miller's test. However, things are not so good for 6. if we do 6 and do exactly the same calculations for 6, we discover that actually 6 passes Miller's test, even though 217, sorry, I'm using wrong numbers. 217 passes Miller's test to base 6, I should have said. Because when we use base 6, when we take A to be 6, 217 behaves as if it's a prime number. It certainly satisfies Fermat's little theorem, that's the one in the first position. But when we keep taking square roots, we keep getting 1 until we get to the last stage, but then we get -1, which is, it could be that, even if we had a prime number, we could get that. So we can't see anything in this column that denies the fact that we don't, it's looking as if we have a prime number here. The column is behaving as if we have a prime number, but we don't have a prime number. That's the setup. Okay, so last comments here. So just to confirm what I'm saying and some sort of fancy language, you don't really need to know this. You should know what Miller's test is and should be able to apply Miller's test by taking these square roots. In practice, when you do the calculations, it's much easier to actually start at the bottom of the table. So I would be inclined, if I'm given an integer and I want to work out whether it passes Miller's test, I would try to divide, I would take n-1, remember this is n-1 here, I keep dividing it by successive powers of 2 until I get an odd number, and then I would start by computing a to that power, because this will be the smallest exponent, it's the easiest to compute. So if I were doing, say, to base 5, I would compute 5 to the 27, and that's not a difficult thing to do, and I discover that the result is not plus or minus 1 mod 217. So I discover immediately that this number fails Miller's test to base 5. Or if I were doing base 6, I'd discover the -1 and this passes. The rest must be okay, because when you square -1, you get 1, and all these would be 1. So that number, put that to that base, it's passed Miller's test. Anyway, just to repeat the what I said before, so there's some fancy language here. Namely, we have really 2 tests. We started with Fermat's little theorem, and we asked ourselves, is a to the n-1 congruent to 1 mod n? And if it is, that number n is called a pseudo-prime to the base you're talking about. So because there are 2 1s here, we would say that 217 is a pseudo-prime to base 5 and base 6. But other exponents, at least the ones we've shown, show you that 217 is not a prime number. They're what are called witnesses to the fact that 217 is a composite number. It's not a prime number. In fact, I think you can go up to about 24, and you won't get ones. You won't get ones for many other exponents. On the other hand, as far as Miller's test is concerned, to base 6, 217 passes Miller's test to base 6. So it really does behave as it's a prime number, not just in the first row, but in all the rows. So we say it's a strong pseudo-prime. Strong refers to Miller's test, whereas pseudo-prime on its own, the word pseudo-prime on its own refers to Fermat. So 217 is a strong pseudo-prime to base 6, not to base 2 or 3 or 4, but to base 6. And 6 is a liar. 6 is lying about the status of 217. Base 6 is lying because it seems to be all okay, but it's not. 217 is not a prime number, even though the column under 6 seems to suggest it is. So we say 6 is a liar. On the other hand, 5 is a witness, because 5 does show you with Miller's test that 217 is not prime. So 5 is a witness to the fact via Miller's test that 217 is not prime. One final remark, just to show you how fantastically powerful Miller's test is. If you just apply it to bases 2 and 3, if you apply Miller's test, that's going a bit further than Fermat's little theorem, because we're taking these square roots of a to the n minus 1. If you apply Miller's test, just to bases 2 and 3, for which it's relatively easy to compute these exponents, you'll discover it will accurately detect all the prime numbers up to 1 million. I believe that's true. I haven't checked it myself, but I believe that. So it's a very powerful test. And in practice, I believe that choosing prime numbers or probable prime numbers to use for RSA are based on fancier versions of Miller's test involving maybe probabilistic estimates. So that's the end of the module. As I say, I'll be discussing what you need to know for the exam and helping you prepare for that after Easter. But I hope you can relax for the time being and have a break from your work this semester. Bye-bye.